Okay, well, thank you for the opportunity to come and speak to you today. I'm sorry that I couldn't come in person, but it is excellent to see that we've been able to organize this. Now, what I want to talk to you today about is some work I've been doing on the filament structure of random waves. Now, random waves they came into being from a more physics perspective as a suggestion of what might be a good approximation to a quantum chaotic system. I have to apologize for a moment. My screen has frozen. There we go. We can move on to the next slide. So this was suggested by Berry, and it's meant to be a model of what a chaotic system might look like. Now, in this case, we look at functions u that are a sum of plane waves. So these plane waves, they have frequency 1 on h, and they're oscillating in direction xij. So you should think of xij as being either a element of the unit sphere or a approximation of the unit sphere. So something close to that. Now, the CJs, those are the coefficients. These are how we inject the randomness. So we pick those according to some random distribution. And there are a couple of different distributions we could use. So we could have Gaussian uniform. We could have uniform on a high dimensional sphere. So these are the kind of options that we have. And for this work, I'm going to choose Gaussian, and each one of the CJ is going to be Gaussian with sigma squared equal to n inverse. So n inverse is the number of waves that I'm summing up. And I need to pick a normalization, and my normalization is chosen so that if I integrate them over the ball of radius 1 and take the expectation, that just returns the volume of the ball of radius 1. So this allows me a sort of a natural sense of what should be size 1. And when I'm going to be talking about various random variables, I'm going to be always comparing them to the volume of the ball of radius 1. Okay, so I seem to be having some issues here. So I seem to be having some issues progressing slides in slideshow. What I'm going to do is going to try and take myself out of slideshow and just scroll through the slides. So hopefully if you give me a minute, my system might fix itself. Okay, that's a little bit better. So sorry, this is not the most effective way to do it in the slideshow, but I don't want to have my screen freezing every time I want to advance a slide. So this is a picture of numerical waves, and this was done by Alex Barnett. And you can see here, this is for very high frequency. So you've got this kind of blur of green, which is average value, and then you have some fluctuations from that average value. So you have points at which the size of the eigenvalue, the size of the function is larger than average. And you can see that they form sort of lines and structures in the set. And so that's the question when I'm talking about structure or filament structure in the random waves. This is what I'm talking about. These are the filaments. So the question then is, what is actually happening? And there are a number of different opinions on this. So some people thought that this was just a numerical artifact. So it should actually all just be a sea of green, but we're just accidentally seeing some numerical artifact when we do our numerical simulations. On the other side, there were people who thought that this was really actual scarring along the lines. And so what that would mean would be that as you take the limit, as you get your frequency higher and higher and higher, you would actually get some lines which the size of the value of u would be much, much larger than expected along those lines. And then a sort of intermediate thing is saying, well, there's probably something, but we tend to see a pattern because we're humans, and we need to take that into account. Now, a major problem with working out what we're seeing here is with the numerical work, anything that we're seeing, any enhancements have to be logarithmic, because we have an upper bound we knew already for Van der Kam and Zeldich, which said that the expectation of U can only grow logarithmically. Now, that would mean that any kind of enhancement would only be logarithmically over what we might expect. And so that makes it very difficult to see numerically, because it's difficult to see a logarithmic enhancement when we're running at small frequency, and we have to run at small frequency because of computational demands. So here are some results, some things that we do know. So firstly, if we fix an X and then compute the expectation. So this is taking the expectation of a value of U of X. So that expectation is 1, exactly equal to 1 under this normalization. On the other hand, we also have a result by Burke and LeBeau, which says that the expectation of the L infinity norm is bounded below by log 1 on H. So as H goes to 0, this term, this log 1 on H, is growing. So it says that the expectation has to grow as you get higher and higher frequency. And we also knew previously that it can't grow more than logarithmically. So this is kind of a sharp bound. So what this says is that if you produce a random wave, you expect that there will be some bright spots, but if you pick a particular spot and then check the random wave, it's unlikely that you happen to pick a bright spot. So this is a difference between some bright spots and each spot will be bright. Now, we dug a bit deeper into this and started to look at equidistribution on balls. So this is results from me and a combination of other people. And what we're looking at here are small balls. So we're thinking about a ball of radius r about p, where the radius of the ball is going to 0 as the frequency is getting larger and larger and larger. And so the idea is, what is the expectation of U integrated over the ball? Now, if radius is 1, I've fixed that by my normalization so that the expectation over that ball is exactly equal to 1. So these are what the results for the small balls. And the result basically says if you're past Planck scale, so this is r greater than h to the 1 minus epsilon. So h to the 1 is your Planck scale, and that's the uncertainty principle. Once you get down beyond h, you can't really say anything because the uncertainty principle says you can just never really tell. So this tells us an equidistribution result. It says that the expectation, the average, is equal to the volume plus something small, and the variance is small with respect to the volume. So that means that if we fix a ball, we take the expectation, we have high probability that we will come up with an equidistributed function in there. So the mass, the L2 mass, will be equal to the volume most of the time. And because we're looking at Gaussian variables, once you're beyond 1 standard deviation, you start to get this really nice exponential decay. So it's, in fact, very high probability. But we want to look at the difference between equidistribution and uniform equidistribution. And talking about things like balls is a good way to see it. So say we have some variable x that depends. So x is a random variable, but it has a parameter as well. So for instance, the ball of radius r about p has 2 parameters, p, the center of the ball, and r, the radius. It then has its randomization as well. So we say that it is equidistributed if the expectation of that random variable is equal to its average equidistributed value plus something that decays as you go in your limit, as h goes to 0, and the variance decays in a scale of the average squared. So this means that the variance is small with respect to the expectation. So that's equidistributed. Uniform equidistributed you want it to be equidistributed for every value of the parameter simultaneously. So what you want to do is you want to look at your parameter W and ask, what is the probability of the set so that you exceed the average value? So in this set, I look at random variables that exceed the average value, and I put some measure on how much I must exceed the average value. But I'm not just talking at a particular point, it's I can find some W, some parameter for which I exceed the average value. So this is where the uniformity comes in. We're not looking at just one point, but we're looking at all points. So for balls, you might be looking at all balls with a particular fixed radius and the point, their center, being able to move. And for uniform equidistribution, you want to show that the probability of this set goes to 0. And ideally, it should be going to zero exponentially. And so that's a stronger form of equidistribution. So now the first way that you could have filament structure is that really strong statement that you actually get scarring along the lines. And so that would be if I took the L2 mass of U along the line, if I've got scarring, that has to be big compared to the average value. So the way I measure this is I set my normalization so that the average value along the line is 1. And then I ask, for what lines could I possibly have something that is much, much bigger than 1? So put into the realm of random variables, this means I set my random variable f equal to the L2 mass of U on gamma. And then I ask, where is the expectation of the L infinity norm of f greater than 1? So L infinity is taken in the parameters x and xi. So x is your base point of your line and xi is the direction. Now I'll assume that all of my lines are length 1. So look over all of your base points and all of your directions and ask, are any of the lines big? So that's quite different than fixing a line and then asking if that one is big. You're just asking if some of them are big. And so what I was able to show is this doesn't happen. F is uniformly equidistributed in x and xi. So there are no strong scars. And so that's the first bit of information that we have. Strong scarring is not what is happening here. And I'll just give you an idea of how we prove this. So the idea here is we need to measure the size of the exception set. So this is a set for which you don't have equidistribution. And x and xi, that's a continuous variable. So we turn it from a continuous variable to a discrete variable by putting a grid on our space. And the idea is that everything is oscillating at frequency 1 on h. So once you get to really, really small scales, much, much smaller than h, things can't change very much. So I put on my grid and I say, well, if I exceed 1 at a point x, xi, I can find a grid point nearby at which I exceed 1 as well. So my exception set, my continuous exception set, is contained inside a discrete exception set. And the number of terms in this discrete exception set grows polynomially, but each of the terms has an exponential decay in its probability. And so I win because exponential decay beats out the polynomial growth. And that's a fairly standard way of proving uniform equidistribution. Okay, so you set up your grid, you prove that in your parameter, if you're exceeding the equidistributed value at one point, you must be exceeding it somewhere on the grid. And therefore, you can reduce your continuous problem to a discrete problem and look at the various decay rates. But this isn't the full picture. I wanted to also look at what we'll call a phase space picture. So the lines, this is just configuration space. It just says physically, where is the concentration? But I should also look at phase space, and that this asks the question, where is it? But also in what direction could you be concentrated? Okay, and so this is a much more subtle question, but it also gives you a much greater depth of understanding of what's going on. So I define a new random variable. And so this random variable is G, alpha, mu, x, xi. So there are 4 parameters of importance here. And it's given by taking an L2 mass of U, where I've applied an operator P. Now, I'm not going to define exactly what the operator P is, but I'm going to describe generally what it does. So the idea of the operator P is it restricts the Fourier support in a h to the alpha region. So there's a relationship between xi and the scale h. Okay, so you come in and you put a cutoff function on where the Fourier transform can be. Then you also want to look in configuration space at some localization. You can't completely localize because of the uncertainty principle, but the uncertainty principle also tells you that you could close to localize in a h to the 1 minus 2 alpha, h to the 1 minus alpha little box. And what I mean by this is outside the box, you have rapid decay. So it isn't quite 0, but it's small enough that you don't really worry about it. So I'll put on a cutoff function on this little box, and then I use an extra parameter mu to measure how far I am away from Planck scale. So mu is equal to 1 is exactly at Planck scale. So this is as tight as I can make it without violating the uncertainty principle. So I can't go any further than that. As I make mu bigger, I'm relaxing my concentration. I'm moving further and further away from the Planck scale. And I pick a normalization so that this thing is equal to 1 if we are equidistributed. And then we ask a question, is this thing equidistributed? Is it uniform equidistributed? So if you fix xi, it is equidistributed. It's reasonably easy to show that the expectation of g squared is actually equal to 1. But you get some interesting things when instead of looking at equidistribution at a fixed point, you look at the uniform equidistribution in x and xi. So this is moving into the more complex picture where we want to ask about some points x and xi where this thing is big. So if mu is big enough, so h to the minus epsilon, so this means h is going to 0. So if this would mean that mu is going to infinity. So we're well away from Planck scale. And if we can do that, we follow exactly the same process as the X-ray variable. And we find that we have a probability bound on the exception set that is exponentially decaying. So this means that once we're away from Planck scale, the answer is that this thing uniformly equidistributes. And it not only does that, it does it at an exponential rate. However, the interesting things happen when we get up to Planck scale. So once you go up to Planck scale, so that's mu is equal to 1, you get a result that says the expectation grows logarithmically by looking at an L infinity norm, logarithmically in the value 1 on h. So what this is saying is if you're down at the Planck scale, there are some points x and xi that are large. Okay, not all points will be large. If I fix a point and take the expectation, that's not going to be large. But for every random wave I generate, there will be some large points. And so if I was to try and see that, what I would be seeing that as, because of the uncertainty principle, if you're big at one point in phase space, you have to be big at all other points nearby. So instead of having bright points like you might for the values of the function, you have smears in phase space that take up some little region and are oriented along the direction. So this would be oriented along this, if this is the E1 direction, and the smear, the size of the smear would be determined by the uncertainty principle. And you should see this as analogous to the Berkeley-Bow result I showed you before. The Berkeley-Bow result said that the expectation of the L infinity norm of U was bounded above and below by logarithmic growth. Okay, so that's just the value of the function at a point. This one tells you that if you look up in phase space, you have the same result so long as you're at Planck scale and you're really tight up until that uncertainty principle. Once you move away from the uncertainty principle, you go back to something that is uniformly equidistributed. Okay, so I'm going to just give you a quick idea of how we prove this. So we prove it by, we're going to prove something about an L infinity norm, but how we do it is we find an LP norm which upper and lower bounds the L infinity norm. And to do that, we have to make the LP norm depend on H. And if you sort of go through all the numerology, you find that you need pH to grow logarithmically in H. And if you can do that, you can bound above and below for the L infinity norm. And again, this is using the whole thing that everything is oscillating at frequency 1 on H. And that's always underlying all of these arguments. So what we do is we then directly compute the expectation of the LP H norm to the power pH. And you can just assume that pH is even because you want it to be large. So it's a bit messy to write out, but this thing can be really explicitly calculated. And so the key computation is to reduce it to a bilinear form with some function with a matrix A here and show that A has a large eigenvalue. And that gives you your lower bound. Essentially, the eigenvalue itself is what is the lower bound there. So once we've done that, you use a measure concentration, because I actually want the expectation of the LPH norm, not the LPH to the power pH norm. But if you have a reasonably concentrated distribution for your coefficients, and the Gaussian distribution definitely does that, you can very much compute the pH power, and from that get the answer for the correct LP norm. So finally, just some thoughts about what is actually happening here. So obviously we don't have strong scars, but equally obviously it is not just a numerical artifact, because there is something happening. I would expect to see correlation between the bright spots and the bright smears. So if you have a bright spot, you would expect to see a bright smear near it if you lifted up and looked at the phase space picture. And you would expect also that multiple bright spots might line up along the smear in phase space. So what I think is happening here is that we are seeing a configuration space echo of what is happening in the more complicated phase space, which we can't plot directly. But there's still quite a bit of ongoing work to work out exactly what is happening. What are these correlations? Can we prove some kind of estimate on the correlations? Is there some kind of fractal structure, fractal dimension of the filament structure that we've found? So I will finish there and hope that you have some questions.
Okay, so thank you very much, Melissa, for this wonderful talk. Are there any questions?
So there's one question come through the chat, which I'll answer. I'll just read it. It says, can I explain in more detail about the coefficient Cj and how they're chosen randomly? So there are numbers of ways that you can choose the coefficient. A common one, which is the one that I've been doing, is Gaussian. So each Cj is chosen as a Gaussian random variable, and they're independent of each other. Another really common one is to choose them non-independently, but uniformly on a large dimensional sphere. So in that case, you will get that the L2 norm of the coefficients is always fixed, which is nice. For the Gaussian, you don't have that, but you lose the independence that you have for the Gaussian. However, it turns out if you're dealing with a large enough sum, that those two random distributions behave very, very similarly. They both have that exponential decay around their first standard deviation. The second part of the question asks about the expectation. How large of the eigenvalues be in the matrix A? So this matrix A, if we're equidistributed, we'd expect eigenvalues of about 1. But we find that there are ones that are growing logarithmically, and it's those ones that drive the logarithmic filament structure.
Are there any
that was all
questions?
from the chat.
So there are no more questions on chat. So are there any other questions? Okay, since there are no questions, we will thank the speaker once again.